and earthquake. It's the longest, heaviest, and most expensive suspension bridge ever built. Now, the world's longest bridge on Modern Marvels. It's one of the most violent waterways in the world. Racked by typhoons, cursed with driving seas, and with currents reaching 15 feet per second, it's the Akashi Strait in Japan's inland sea. Long a major barrier to uniting northern and southern Japan, this 2.5-mile watery divide is now spanned by the mightiest bridge in the world. The most technologically advanced suspension design ever built, the Akashi-Kaikyo Bridge.
The Japanese were presented with a very interesting challenge in the Akashi Straits. It's a relatively narrow strait. It's a major shipping channel. 1,400 commercial vessels that pass through the straits every single day. Coupled with that, then, is the currents or the flow of water through the Akashi Straits.
The Akashi Channel was a major challenge to Japan's bridge builders. The strait is over 360 feet deep. The intense currents that course through it cause violent flows at the surface and rapid erosion on the seabed. It is crowded with both fast-moving freight and stationary fishing vessels. And in the center of this, the engineers proposed to situate two nearly 1,000-foot high bridge towers and join them with a record-breaking 12,828-foot span, which would link north to south.
Economic development is very important to the Japanese, and of course the populated areas of Tokyo and Osaka have the population density. The Japanese want to open up for economic development many of the other parts of their country, and so to do that they have to get from the population centers out into what was once the hinterlands. And so they established a transportation network comprised largely of rail and highway. The Japanese take that experience that they developed on the other bridges that they built in the Honshu Shikoku Bridge projects, leading to what is now the longest suspension bridge in the world.
These many bridge projects have all been designed to face a final immense challenge: earthquakes, and of all the natural enemies posed by the environment of Japan, none is so feared or deadly as the quakes that shake the island nation frequently. Most of them are small, passing almost unnoticed. But on the early morning of January 17, 1995, the Great Kobe earthquake crashed through the Akashi Strait into the slumbering city.
Then the Kobe earthquake occurred. When we surveyed the central line of the bridge, we discovered that it was slightly off the straight line.
Today, this magnificent bridge connects the main island of Japan with its southern cousins. Traffic crosses its 6 lanes day and night in all kinds of weather. And below, hundreds of ships carrying all kinds of commercial cargo pass unimpeded. But it was not always so. Early in its history, Japan was a nation divided by and bounded by water. In the mid-1800s, attempts were made to bring Japan into parity with the West. And smaller vessels often fell victim to the whims of weather and sea conditions. By the late 1800s, Japanese engineers were traveling to the United States and Great Britain to observe the building of some of the great suspension bridges of that time, including the Brooklyn Bridge in New York. They took this expertise home to Japan, but it would be nearly 60 years before it would be put into practice on very large projects. By the late 1930s, plans for large-scale bridge construction were on the drawing boards. But World War II would divert resources, manpower, and willpower from the task. By the time it was over, 2 million of Japan's sons and daughters were gone, and the nation lay in ruins.
All of their efforts really began post-World War II. The Japanese began their quest for building large bridges and structures spanning the straits, spanning the waters, the seas of Japan. in about the early 1950s. And what the Japanese do is they take a large project and they research it, they practice, they build that bridge, and from that bridge they learn a lot more. They take that experience that they developed on that bridge and they turn it into the other bridges that they built in the Honshu-Shikoku bridge projects.
In the 1950s, the future of Japan's economy depended on linking the country's sprawling infrastructure.
We need the infrastructures. We have so many islands separated by sea, so that in order to connect each side, we need bridges.
But the seaways of Japan would not be easily bridged. Many of these waters, the prime lifeline of commerce for the island nation, are infamous for their strong currents and foul weather. This made boat traffic unreliable, but building a bridge to replace it seemed a daunting task. While other narrower routes between the islands had been spanned by bridges, by the late 1980s, the Akashi Strait was still served by ferryboat. The government wanted to open this one last key route to the south, if they could.
The Akashi Bridge is just a huge project that had never been attempted from the magnitude of scale. So a lot of the technologies that worked before, a lot of the standard construction technologies, a lot of the design criteria had to be modified, had to be redeveloped, and had to be tailored specifically to this creation, the Akashi Bridge.
Bridging the treacherous Akashi Strait was easier said than done. Home to both severe wind and waves, a bridge here would have to be designed to withstand the worst of these combined forces. The Akashi-Kaikyo Bridge would be the last and longest span in this violent environment. But what kind of bridge should be built?
When looking at span lengths so great, over 1 kilometer, a suspension bridge is the only viable structural type capable of spanning such great distances.
But structural considerations were not the only challenge. Japan is a country with a keenly developed sense of the aesthetic, and this applied to the bridge design as well.
The Japanese are very, very conscious about the environmental aspects of construction, and they are very, very conscientious about the aesthetics of any of their projects that they do. The government and the population wanted a bridge that blended and fit into the environment. I think most anyone would acknowledge that the form of a suspension bridge is perhaps one of the most magnificent shapes and forms of any kind of bridge that you could possibly design.
The 2.5-mile span would be crossed with a suspension bridge. With this determination made, they had one other major design concern: earthquakes.
Japan as a whole is seismically extremely active. It's on the Pacific Rim, so the Pacific plate is rotating by about 2 inches every year. And so this causes then earthquakes along the entire Pacific Rim, and so Japan is prone to see a lot of earthquakes. Also the site where the Akashi-Kaikyo Bridge is clearly exposed to seismic threats.
So it was recognized that there was a fault running through the straits there. It runs along the periphery of the city of Kobe. It wasn't thought to be a very important fault at the time of the first construction of the bridge.
To ensure a safe design, bridge planners carried out extensive testing.
As the Japanese investigated seismic design, they relied very heavily on computational models. The advent of the computer was just one of the marvels of recent time. Computational power is, without a doubt, saving grace for being able to design these huge structures. And so computationally is the best way to investigate the seismic performance and seismic behavior.
The data looked promising. The computers had vetted the most critical design considerations. A bridge across the Akashi Strait looked possible, but now they had to build it. Among its other records, the Akashi-Kaikyo Bridge is also one of the most expensive to cross, at over $20 per vehicle. The world's longest bridge will return on Modern Marvels. Suspension bridges are in their simplest form, huge horizontal decks hanging from overhead cables. These cables must be supported by the shoreline. To do this, giant anchoring points, or anchorages, must be fabricated. This was the first step to creating the Akashi-Kaikyo Bridge.
When you design a suspension bridge, whatever the total weight of the bridge is, it has to be carried in those anchorages. If you've got 1,000 pounds you're carrying, it's not inconceivable that the size of the anchorage, the mass of the anchorage, because that's what resists the total load, would be 10 times the amount.
One of these gigantic structures would be built on the Kobe side of the strait, the other on the Awaji Island side. Each location posed specific challenges. The first major problem was to get down to hard rock for a firm foundation on which to build. But bedrock was a scarce commodity in the area.
Typically, we go far enough down that we do find sufficiently strong material to support then the structure.
In fact, only the southern anchorage on Awaji Island would actually touch bedrock. The rest of the bridge's supporting structures were all built onto gravelly alluvium, or atop loose strata. The huge pit for the north anchorage was excavated to a depth of about 200 feet. Once the dig was complete, the pit wall was prepared by installing a retaining wall. This 8-foot thick wall held back the dirt around the pit. Then the pouring of the foundation concrete would begin.
When the excavation process is finished and we reach the bottom, we fill the lower compacted concrete inside. In 3 months, we finished up to within 6 meters of ground level. Then we put down steel reinforcement.
300,000 tons of concrete were poured into the pit, making it the biggest structure of its kind on record. The concrete was poured in steps to allow each layer to be tamped by steamroller, and also to avoid a common problem encountered in building large concrete structures: heating.
You need to cool down large masses of concrete when you pour them. Otherwise, you get already, just from the shrinkage in the concrete, during the curing process, you get a lot of cracking in the concrete.
Once the foundation was poured, steel reinforcement in the top layer would provide connecting points for the huge anchorage tower to be placed on top. This structure was brought in as one pre-assembled unit by barge-mounted crane.
Since it was close to the ocean, the frames were made in a factory and transported by a floating crane and erected at once. After that, the anchor frames were set in place. To do this, we used a high-performance concrete.
The framework in the anchorage structure was so intricate that traditional concrete would have had trouble flowing between the frame members. So a new, highly fluid concrete was developed that would flow easily throughout the structure. From the top protruded the cable anchorage frame. This provided the points with which the huge suspension cables would later mate.
If you were to look at the anchorage, you will see that there's the splay block, and then those cables are separated of the main cable and individually anchored inside that anchorage frame.
Once locked to the anchorage, the bridge would transmit most of its weight there. If anything went wrong here, the bridge would collapse instantly. When the last batch of concrete was poured and the anchorage proclaimed complete, the workers held the first of many celebrations. The south anchorage on Awaji Island was built using the same methodologies, but the pit was only about 60 feet deep and rested atop granite bedrock. Next, far from the safety of shore, came the towers. The towers for the Akashi-Kaikyo Bridge alone required 2 major contractors each. The design of the foundations for the 2 towers, which were to be constructed in the 200-foot deep waters of the channel, would be critical.
Whether it be for the earthquakes, whether it be for the typhoons that come along frequently in Japan, the high winds, the rain, the treacherous torrents of the waters within the straits of Akashi, all of those features had to be accommodated in design and in construction.
The channel between the anchorages was deep and gravel-lined with bedrock far below the point where excavation for tower foundations would be practical. But the builders wanted to find the most stable surface possible, and these towers would be the biggest in the world, at 930 feet in height. The solution would involve setting a huge steel cylinder known as a caisson onto the gravelly bottom to provide a strong, stable footprint for each tower.
The caissons are approximately 65 meters or so below sea level, and they are approximately 80 meters in diameter. They're huge. The Japanese had to accommodate, number one, the tidal currents, which were as much as 4.5 meters per second. What they decided to do was to actually prefabricate huge double-walled steel caissons, 2 of them, 1 for each tower. And they built those steel caissons on the fabrication plant.
Each 19,000-ton caisson would be sunk and filled with concrete to supply a firm base. But resting on gravel introduced other problems, such as scouring, where the swift currents would wash out the gravel beneath the caisson.
Since I knew that the prevention of scouring was the greatest challenge, we conducted laboratory tests with 1/100 scale models for almost 3 years. As a result of the test, we determined that the anti-scouring measure would be to install 80-meter wide ripraps around the caisson.
Riprap is a term from mounds of large rocks, which would surround the caisson on the sea floor. First, the sea floor would be dredged using a traditional floating dredging unit. Then, once a circular hole was made, the caisson could be sunk. The rocks, or riprap, would be dropped around the caisson. But there was still a problem.
With stones of that size, the sand between them would get sucked up. To deal with that problem, we came up with filter units.
These filter units were bags of smaller rock that would sit atop the other stones, forcing the water to flow through them. This either diverted or slowed the flow of water to the point that the scouring or removal of seabed was practically eliminated. The caissons would be able to sit on a gravelly bottom without losing their footing and twisting out of position. Tests showed this approach to be sound. Now the caissons had to be completed and towed into position for sinking.
The caisson, which is 80 meters in diameter, is divided into two sections, the double wall and the inner core. The area of the inner core is about 2,500 cubic meters. We conducted training for the submerging process at Shodo Island for about a month. Then we picked a day with the smallest current to tow it there. As I said earlier, this caisson has a double wall. That became the buoyancy tank, which made it possible to float.
The enormous caisson was ready to head out to the choppy seas of the Akashi Strait. It would be the largest structure of its kind ever towed through these waters, and would face the dual threats of fierce winds and driving seas. The Akashi-Kaikyo Bridge is almost 4 times as long as the Brooklyn Bridge, or 8 times as long as the Sears Tower is high. The world's longest bridge will return on Modern Marvels. Central Japan, the turbulent Akashi Strait. On a clear March day in 1989, 12 powerful tugboats began the perilous job of towing the giant caisson, the first of 2 to the job site. Once it was centered over the prepared seabed, special cables were connected between the caisson and numerous huge anchors on the seafloor. These anchors had been dropped in a circle around the prepared pit in the seabed and would help to guide the caisson into the proper position as it sank.
We pulled out a cable from the winch on the top of the sinker, or anchor, which was already on the seabed, almost 1,000 tons each, and connected it.
This was quite an achievement in itself because you have effectively a cork bobbing in the water and you're trying to hit a perfect spot, and through the use of GPS and positioning systems and ballast and weight, they slowly could sink that caisson down to the prepared seabed.
We started the submerging process the next day at low tide. The submerging work was done by pumping seawater into the core part and lowering it straight down. There was a monitor on the caisson, and we measured the positioning of the caisson and maneuvered the cables. Then, about 1 meter from the seabed, we sank it, with about a 2-centimeter error.
The huge caisson now rested on the seafloor. Soon the other one at the south end of the channel would follow. Now, final preparations had to be performed on the silty muck that they covered.
There were some more residues that the grab excavation could not pick up. After submerging the caisson, we used an underwater robot called Airlift to suck up some rocks and rubble.
But once firmly on the bottom, the huge can had to be filled with something other than seawater to make it heavy.
Once that caisson was in place, all of the water was pumped out and it was replaced by special underwater concrete.
This was a new way of doing business for bridge builders. Traditionally, caissons had been sunk, pumped out, and then men sent inside to work. Danger was a constant companion, and many perished. But this caisson had been sunk onto a prepared seafloor, and the only thing entering it would be this special concrete. But because the entire structure would be submerged, the Japanese needed a concrete that could settle and cure underwater. Enormous concrete plants were floated to the caisson on barges.
The ingredients were mixed and then pumped in to displace the water.
Each layer poured used up most of the raw materials on the barge. As this mixture hardened underwater, the construction crews would wait for the next favorable tide. The average wait was 2 weeks.
Ultimately, that whole 80-meter diameter caisson, which is about 70 meters high, was filled completely with concrete. And then a special table or top was placed on that caisson, about 10 more meters of concrete, into which was anchored the tower bases themselves. Once the steel tower bases were cast into that tabletop, then the erection of the towers began.
The height of this tower is about 300 meters, 1,000 feet. One of the most important issues for the design of this tower is wind-resistant design. Because the tower is very high, so it is relatively flexible and easy to vibrate due to the wind.
Many tower designs were considered. The design chosen was a so-called cruciform, where X-braces would support the openings between the vertical supports.
The purpose of that is really for aerodynamic stability. It was the most forgiving shape to accommodate the strong forces of the very strong winds that occur.
The tower design also had to incorporate one more major design component. The two towers had to be able to withstand Japan's frequent and often mighty earthquakes.
From a seismic point of view, it's primarily the towers. That's the next or the most critical element, because the towers support the cables. If there are failures, we could see the towers getting overloaded, the local buckling of the steel towers at the base. These are the kind of critical conditions we are designing these structures for.
Each of the 930-foot-high towers was prefabricated at one of 12 factories across Japan. They had to match each other perfectly. Cooperation was critical. Tolerances needed to be very precise to assure a truly vertical structure.
Tower one shaft consists of 30 blocks vertically. Both sides of the blocks are polished. So because one of the most important things for the tower is vertical accuracy.
Each tower component was hauled to the worksite by a huge barge-mounted crane.
We use a large tower crane with a capacity of 160 tons, and with that crane we put each block by block.
The slightest deviation would be magnified as the towers reached skyward.
The tower must be perfectly vertical, so you do not induce extraneous forces into the tower as the cables pull one way or another on the towers themselves. What that translates to is about an inch out of plumb over 900 feet high. So in order to achieve that accuracy, tremendous tolerances had to be met. They were perfectly matched so that when you put one on top of the other, that mating surface is absolutely perfect.
As the construction progressed, the engineers were required to check the fit on each side of each block of the tower.
Feeler gauges, little shims were used, and the acceptance was that you could not put that shim or feeler gauge between the mating surfaces of one block when stacked on top of another.
In essence, the clearance between the tower blocks had to be thinner than a playing card to pass inspection. If not, the block would have to be returned to the factory to be further refined. But none were. The workmanship was that precise. The weather, however, was not so accommodating.
That was a thunderstorm. In December of 1992, the northern tower was almost completed, and this southern tower is about 200 meters high or something. And that time there was a very large thunderstorm. It broke the measuring equipment on the cranes on the northern tower, and we have to stop the construction work about 3 weeks.
In fact, between heavy rain, typhoons, and rough seas, construction was able to progress only about 6 days in 10. But this had been factored into the schedule, so the overall delay was minimal. Soon, the towers soared gracefully into the skies above the Akashi Strait. But there was one more important device used to ensure they stayed there.
We decided to put the tuned mass dampers inside the tower. This is one of the most important things for these towers.
Tuned mass dampers are huge weights that counteract the forces of wind or high loads on the bridge. With constant input from computers, which are in turn wired to sensors throughout the bridge, the tuned mass dampers can be set to rock in a direction and at a frequency that will offset the sway inherent in such tall towers. 20 were installed in each tower and worked 24/7 to keep the structures upright. With the giant towers complete, the next gargantuan task loomed before them: stringing the 3-foot diameter steel cables. At 350,000 tons, the north anchorage of the Akashi-Kaikyo Bridge weighs nearly as much as 4 of America's largest aircraft carriers. The world's longest bridge will return on Modern Marvels. The spine of a suspension bridge is its cable. No other component is so graceful or so apparent. And none other is so crucial to the continuing success of a long-span bridge. Making the right choices for cabling was one of the greatest challenges facing the designers of the Akashi-Kaikyo Bridge.
The difficulty is that if they use traditional materials, instead of having one main 1.1 meter diameter cable on each side of the bridge, they would have to have 2 cables because the material was not strong enough. What the Japanese did was to develop a higher strength wire strand. It was about 12% higher than had been used in traditional cable construction for suspension bridges.
In order to increase cable strength, we reviewed the components of the cables and were able to enhance the cable strength by increasing the amount of silicone in it. The structure of the cables is seen here. It is a bundle of 127 wires of 5 millimeters in diameter. This is called a strand. 290 of these strands make up the cables for the Akashi-Kaikyo Bridge, 36,000 wires.
These strands were then rolled up on tremendously large spools and then stored at the fabrication site. Now the problem becomes, how do you erect the suspension cable? The Japanese did not want to interrupt the flow of commerce, 1,400 vehicles a day through the Akashi Straits. They wanted a means of erecting the cable such that there would be absolutely no inconvenience to the commercial user of the Akashi Straits. What they did was they decided to go to something called prefabricated wire system.
With the immense reels of cables sitting at the water's edge, a unique system was needed to sling the cables across the bridge. They chose a non-invasive procedure to pull the first cable strand across the strait.
What the Japanese did was they went to these new high-tech materials, to a fiber composite material. It's called an aramid, about a 1/4 of an inch diameter cable. Very, very lightweight, very, very strong. The helicopter actually picked one end of the cable up, took it from one anchorage to the top of the tower, first tower, top of the second tower, and to the second anchorage on the Awaji Island. Other cabling was then added, pulled across the bridge, and that was repeated 290 times because there were 290 of these prefabricated wire strands in each cable.
After 290 strands were erected, we shaped them into a circular form the way it looks now. This process is called squeezing.
The mass of wires was forced into a large circular shape by the cable clamps. Once this had been done, the suspension hanger ropes could be dropped toward the roadbed area. But first, the main cable had to be protected. This too would pioneer new technologies. The huge bundle would be wrapped in yet more steel wire by a special machine that worked tirelessly, like a metal spider. But with the covering over the wire, it was now subjected to the principal enemy of all suspension bridges, corrosion.
That's the big problem, that you don't really know what's going on in the interior. If we have enough wires then corroding and breaking, then it could potentially lead to a collapse of the bridge.
To combat corrosion, the Akashi-Kaikyo Bridge uses two unique lines of defense.
This was the first time we wrapped rubber around the suspension cable, and since rubber is intolerant of ultraviolet rays, we painted the rubber to protect it. The paint was a special blend and the kind that would adhere to rubber.
This sealed the cable bundle against light, wind, moisture, and dirt. But inside the jacketed cable, almost 20% of the total area was still just empty air. How could they keep the inside of the cable dry?
Typically what's done on suspension bridges is a very heavy paste is literally spread over the wires, injected in the wires, and it would tend to fill that 20% of the voids. The Japanese wanted to control the humidity because in the absence of humidity, you can control corrosion. They decided that they would design a dehumidification system for those cables. They would pump air, dry air, throughout the whole main cable, which extends more than 4 kilometers from anchorage to anchorage.
This air must be pumped throughout the main cables 24 hours a day, every day of the year. In this, even more so than with other aspects of the bridge, maintenance is critical.
Inspection of the cable is not easy. We check the cable by using some kind of thermometer and humidimeter. We always checking inside of the cable, keep the relative humidity under 40%.
And this is really kind of unique and ingenious because if corrosion of those cables can be controlled, that will be tremendous savings to the public 75 years, 100 years, 150 years down the line when these cables typically start seeing corrosion-related problems.
The cables were strung the length of the bridge and then tied into the anchorages. Deep inside the anchorage tower is a receiver frame for the cable strands, which are affixed one at a time.
We did not fasten all 36,000 lines in one spot. We placed a socket at the end of the strand, so each socket is fixed separately on the anchorage.
This was repeated 290 times for each cable on each side. As one might expect, security is higher here than at any other site on the bridge. With the towers erected and the cables slung from one anchorage to the other, all that remained was to build the roadbed. But nature had one final deadly challenge to the completion of the Akashi-Kaikyo Bridge, one that could bring about total destruction. The Akashi-Kaikyo Bridge uses over 186,000 miles of wire in its suspension cables, enough to encircle the Earth 7.5 times. The world's longest bridge will return on Modern Marvels. January 17th, 1995. Kobe, Japan is shattered by a magnitude 7.5 earthquake. By evening, 5,000 people are dead or missing. 26,000 are injured, and the city is in flames. 1/6 of the population is homeless. And in the channel, straddling the city-killing fault, is the Akashi-Kaikyo Bridge.
The actual fault went right underneath the bridge. The tower on the Kobe side stood firm. The tower on the Awaji Island side actually moved some 0.8 meters towards Awaji Island, and the anchorage on Awaji Island itself moved 1.2 meters.
The type of fault that we're dealing with is a strike-slip fault, where it's a vertical gash into the earth where one side is moving horizontally past the other side. In this particular case, there seems to have been actually two individual strands of the fault. One that ran into the interior of Japan through Kobe, and then another strand that ran out into Awaji Island. And those two strands more or less come close to each other right beneath the bridge. The epicenter of the earthquake, where the rupture actually started, seems to have been right beneath the bridge.
After the major rescue efforts were complete, attention turned to the Akashi-Kaikyo Bridge, All the tests have been based on a magnitude 8.5 quake, some 100 plus miles inland, but it had never been tested for a quake originating directly beneath it. Had the caisson sunk into the gravelly seabed? Had the towers, now almost 4 feet displaced, been damaged? Could they complete the bridge at all? A thorough inspection showed the bridge structure and cable to be sound. Amid the chaos and destruction of Kobe, this was welcome news. Construction continued anew, a month after the earthquake, in February of 1995. It was time to install the roadway. This too would be accomplished in sections, like the tower modules. Each section was prefabricated on land and staged near the bridge. The truss for the body of the bridge had been carefully designed and tested for many years, via both computer and wind tunnel. Aerodynamics were a major concern because the truss work, more than any other element in the bridge, would be susceptible to the effect of winds.
A lot of the wind tunnel tests have been carried out to measure the aerodynamic forces for evaluation of the flutter instabilities.
In fact, the government built some of the largest wind tunnels in the world, north of Tokyo, specifically to test the effects of high winds on the Akashi-Kaikyo Bridge. A 1/100th scale model was used.
Keep in mind this bridge is 4 kilometers long, so you're looking at about a 40-meter model long. And they actually put this into a turbulent wind generator, and they tested that bridge in scaled wind flow up to, I believe it was 80 meters a second.
They learned that the Akashi-Kaikyo Bridge could bow sideways almost 100 feet before experiencing significant damage. And to do that, the wind would have to be blowing at nearly 200 miles per hour, an unlikely scenario. The design selected for the roadbed, decking, and truss was a cantilevered truss girder. Construction of this last major phase of the bridge began in mid-1995.
The roadbed and the girders are built from the towers out, so that small sections of truss would be brought out, would be put into place, and then the suspender ropes would be attached to that particular panel of truss. Once that panel of truss was then suspended by the suspender cable, they would move on to the next section and bring another truss element out and cantilever off of the previously erected truss segment.
The open girder design was selected to afford great strength without impeding wind flow. The roadbed came next. As the bridge neared completion, the now familiar shape took form.
On top of the truss system, then, you have to place a deck. And basically what that is a steel plate. You come back in and you put a couple of inches of a special kind of asphalt right on top of the steel plate, and you put another couple of inches of a certain type of epoxy asphalt on top of that.
On April 5th, 1998, the massive project was complete. 10 years and nearly $4 billion had gone into the effort. There had been 6 injuries, but because of extensive safety precautions, no fatalities. This impressive safety record stands as a testament to the efforts of the many companies whose fortunes rode on the Akashi-Kaikyo Bridge. By mid-morning, the bridge opened for traffic. 1,500 invited guests were joined by tens of thousands of people from all walks of Japanese society.
I had the opportunity to be at that opening ceremony with the Crown Prince and Princess, and it was an exhilarating experience in just looking at the culmination of probably 30 years worth of work that had gone into the planning, the experimentation, the design, and finally the construction over the last 10 years.
The bridge creates a graceful sweeping arc across the Akashi Strait today. But the Akashi-Kaikyo Bridge may be one of the last huge metal suspension bridges made, as the primary ingredient, steel, reaches the limits of its strength.
That bridge is designed so that 90% of the weight of the bridge supports itself, which means that only 10% of the total weight of the bridge is dedicated to supporting the traffic. Previously, suspension bridges have been designed to accommodate about 25%.
A much longer bridge made of steel would be completely ineffective and could eventually collapse under its own weight.
Clearly, Ideally, we need to look for stronger and lighter materials, since we are chasing primarily the self-weight of the bridge to achieve longer spans.
But for now, the Akashi-Kaikyo, part of a vanishing breed of heavy steel bridges, is a lone sentinel, holding the world's record for the longest single